Okay, so today I'm going to discuss or to show you what we believe may be a new technique, a very simple technique to simplify kinetic studies, kinetic analysis, especially in situations in which there is controversy in the literature about which one is the best kinetic equation, or controversies over the mechanism, or sometimes when you want to do kinetic studies, your statistician tells you, no, you must really use a very wide range of feed composition, temperature, pressure, what you call it. And then sometimes the range is so huge that it affects the surface of your catalyst, and then you are in a different kinetic regime without even realizing that you are in a different one. I think that this theory can be used as a preliminary tool to study the rate of reactions. So, I presented this early this week in Orleans, but I did make some changes that I'm going to show it to you now. First of all, I'm going to make an introduction to the singular kinetic path by means of an analogy, so that the concept will become clear. And then I will show some examples as applied to Fischer-Tropsch, then to some systems with thermodynamic constraints, like the dehydrogenation of ethanol, catalytic cracking of gas oil, and then from these specific cases I'm going to jump to a general application, like A plus 2B goes to C plus D. And then I'm going to close this presentation with some conclusion, and I'm going to tell you some limitation of this theory, the ones that we're aware of at this point in time. So now I will start the analogy, and I will spend quite a bit of time trying to convey the basic idea of the singular kinetic path, because I presented this twice, one in South Africa and one in New Orleans, and I found that the main problem was that the basic approach, the basic message is not really completely understood. Probably it's my fault, but I will try to be more clear with you now. And I want to show you this analogy. Let's say that you're throwing an object into the air, like I'm throwing my pen here. Obviously, if the initial velocity is low, the pen will reach a very small height, not very high. The higher my initial velocity, the higher the pen will go. But the initial velocity from V0 to 0, it doesn't go, it's not that the pen goes slow here, fast here, and slow here. It follows a precise law. A precise law. And the decrease in velocity is a function of the gravity. The final height is a function of the gravity and a function of the linear velocity. So, if you know the initial linear velocity, if you know the gravity, it's very easy with one of these simple equations. You can predict the maximum height that this pen is going to reach, ignoring all other variables. That has a very small effect. You can do that here in the Earth with a gravity of 9.8, or in the surface of the moon, which I think the gravity is 1/6 or something. If you do not know the initial velocity, but let's say somebody is throwing this pen into the air, and let's say you know the gravity, and they tell you after 2 seconds this pen reached, wow, this is crazy. After 3 units of time, the pen reached a 20 centimeter height. What will be the height after 6 units time? Yes, you can do that also by the equation. You can predict, because there is a general path. This pen, the velocity profile of this pen, as it go up, follow a unique function, a singular function, a singular path. Now, what I did here, okay, this is just a representation of what I was talking about. But yesterday at the hotel, I said, how can I present this more clearly now as applied to the singular kinetic part? And I apologize for the poor quality of the transparency, but it was the best I could do. And I use a book to draw a straight line. What I'm plotting here is the heights. The heights H1 and H2. These are these two heights. H1 and H2. H1 after the time T1 and H2 after the time T2. I'm plotting these two heights for different gravities, yeah, and different initial velocities. Now, for instance, the first case, the initial velocity 100 meters per second and the gravity is 9.8. Then I'm saying that after 2 and 4 seconds, after 2 seconds, the height in the first case will be 190, and in the second case it will be 340. Probably it's not precisely 190 and 340, but I forgot the equation for the free fall of body, so I said, well, in the first second it's going to be 100 minus 10, in the second it will be 90, but it's going to be very close to that. Now, the maximum height at those conditions will be 550 meters. And then it will start coming down. So, after 2 seconds, it will have traveled 190 meters, which is 34.5% of the maximum possible height. And after 4 seconds, it went 340 meters, which is 61.8% of the maximum height. Yeah? The second case is very similar, but now the initial velocity is 300 meters per second. In the third case, is 360 meters per second, but the gravity now is 20 instead of 9.8.
Pointer behind the screen.
And in the fourth case, all what I'm changing is the initial velocity and the same gravity. So we have here different initial velocities and two different gravities. Now, if I plot this pair of points, the heights at 2 versus 4 seconds, this must be always constant. Yeah? You can choose 1 and 3, 4 and 5, 5 and 10, but once you have chosen, you must stick with them for all examples, 2 and 4. If I plot the percentage of the maximum heights at 2 seconds versus 4 seconds for all the different cases, what I will obtain is a unique function. This is the percentage of the maximum height at T1, in other words, H1, and this is the percentage of the maximum height at T2, this one here. So, as you can see, I calculated more points, so I only use 4 for this transparency. As you can see, all these points follow into the same curve, irrespective of the initial velocity or irrespective of the gravity. So, please let me know if you understand now this concept clearly. If you plot the height at the time T1 versus the height at the time T2, if you standardize that, you will get a unique function, a single curve, irrespective of the initial velocity or irrespective of the gravity. So, if that point is clear, now we can see how this is applied to kinetics. Now I have to go back to the previous transparency, where I put the T1, T2, and the height. Now let's see what will happen in a chemical reactor. Let's say a fixed bed reactor where the feed goes from the bottom and exits through the top. Okay. You see now, a chemical reactor is sort of similar, we can say that in a chemical reactor, instead of velocity, you have rate of reaction. But at the inlet of the reactor, normally the rate of reaction at the beginning is higher than at the end, because at the end, your reactants have depleted, or you have any other, normally have depleted, so the rate is smaller. So one can say that the rate is equal to the velocity. The higher the initial velocity could be the higher initial rate of reaction. You can achieve a high rate of reaction by different feed composition or a higher temperature, in some cases higher pressure, but the rate of reaction changes. Okay? So one can say that the rate of reaction is sort of equivalent to the initial velocity. Now, but the rate of reaction is not constant along the reactor. Something makes it smaller. Now, normally, let's say you have an isothermal reactor, and let's say the pressure drop is so small that it has a negligible effect on kinetics. What stops the rate of reaction there? It is the change in the composition of the reactants, among other variables. But that's one of the main reasons. Because the reactants becomes products. Normally, your rate equation, your kinetic rate equation, you have the concentration of the reactants in your kinetic equation. Those concentrations become smaller, the rate will become smaller. The rate will decrease. How will the rate decrease? Does it decreases fast here, slow here, fast here? Does it decrease following a zigzag? No, it must follow some monotonic kind of approach. It even decreases linearly, or it decreases like this, but always follow some kind of a logical function. The way in which the rate decreases depends on the interaction between the reactants to become products. That's your rate of reaction. Is how do the reactants interact with each other? And the way in which the reactants interact with each other is your kinetic expression. Then one can assume that the decrease in your rate of reaction is your gravity. It's slowing down your process. And the height will be the conversion. In other words, if you have a high temperature, you have a high initial rate of reaction, which is a high initial velocity. The height with a high initial velocity will be high. In your case, the conversion will be high. If you have a low initial velocity, a low rate at the beginning, your final conversion will be lower than when you have a high initial rate of reaction. So then, in the same manner in which previously we plotted H1 at T1 and H2 at T2, now we're going to plot the conversion. We're going to plot the conversion at a constant ratio. In that case, it's not 4 seconds and 2 seconds, a ratio of 2 to 1, but a ratio of 4 to 1. Why 4 to 1? Because you could use any ratio, but when I was looking at this first, I saw data after in a pilot plant after 3 meters and after 12 meters, so the ratio is 4 to 1. And I started plotting 3 meters versus 12 meters, and then I was stuck with that. And when I went into the literature, I was trying to figure out ratios of 4 to 1. So the ratio 4 to 1 could be in axial position in the reactor, or it could also be retention time, 1 second, 4 seconds, or gas hour space velocity, 4 to 1 ratios. So we're going to do that. We're going to look into in the literature, and we're going to plot the conversion at a ratio of 4 to 1 in residence time for the same reaction, of course. If I was clear enough up to this point, the rest of the presentation is going to be easy. But if you have any questions now, I think I can stop for a moment and answer if this concept is clear. I look at some published data in the literature on fission troughs. I found mainly four main groups: Decker, UOP, Bukur, Satterfield. Basically, there is no logic in selecting these references. It's only whoever published table in which I could extract data with a ratio 4:1 in residence time. That's all what I could find. And this is what I did find. As you can see, there is no Sassel link in these figures. The conversion of hydrogen plus carbon monoxide, the synthesis gas, by the fission Tropsch reaction at the time T1 versus the same conversion at the time T2. Now, all these catalysts belong to the same family, which is it was potassium promoted of some kind, precipitated iron. But they were very different. But in spite of their differences, the family, the general family, was the same. You can see that the correlation is not really that great. There is a few points that are not really in this line. But considering the diversity of the sources and considering the catalysts were not precisely the same, I would say that there is really a trend here. There is some kind of correlation between T1 and T2, the conversions of T1 and the conversion of T2. It's not, as I say, it's not ideal, but really gave us the first indication that maybe this kind of approach could be used for kinetic studies. So the next step was to simulate these conversions. But we wanted to simulate this conversion for many different reactions and reactors. So what we did is we used a very simple kinetic model. I'm almost ashamed to show it to you, but I have to show it to you because otherwise you will ask me where does the data come from. We don't understand. So we put it there. It's a very simple stochastic model. All what it does is the input is temperature, pressure, space velocity, feed composition, and then you can put whatever kinetic expression or expression that you want there. And you can change the exponential constant and the constants. So you can put here input your kinetic equations. And what it does is it calculates based on your kinetic, what it does with the feed composition, let's say you tell the model, okay, this feed is 70% hydrogen and 30% carbon monoxide. So then you just multiply by a factor and tells you maybe 70,000 molecules of hydrogen and 30,000 molecules of carbon monoxide goes into the system. Then it calculates the partial pressures, use them as based on the feed, and then the rate of reaction, calculate the rate of reaction and then subtract the moles that have the molecules that have reacted and adds the molecules that are formed. Like in the carbon monoxide, you lose carbon monoxide by fission troughs and by water gas shift. Yeah? Water, you get water when you have your fission troughs reaction, but you lose water when you have your water gas shift reaction. So in other words, it calculates the new number of moles. In this case, for instance, I'll make 200. It goes through this logic 200 times, which I think is good enough for my case. It gives always a very, very smooth correlations. And then it prints the conversion and the composition every 10 loops, which is also good enough. So then you can make this number of iteration directly proportional with time. But then you can follow the conversion path. Now this simple model has been validated with experimental data. So and actually it's so simple that it works. And then it gives a run for the money to our rigorous models. I can calculate in less than a second, but the rigorous models take quite a lot of time, very close. In other words, I use this simple model to look at the conversion path in some of the cases. then, one of the things that in the literature, there was a lot, I'm sure the ones of you working in fisher troughs are aware of this, is for iron catalyst, there is always a controversy. Which equation should we use? Should we use the Anderson-Dry equation for iron on fisher troughs? But the Satterfield-Huff equation is also good, or there are other equations as well in the literature. Our engineers come to us and they say, which equation should I use? I use this one and it works. I use the other one, it works. Which one should I use to? But they look different. Which one should I use to design my pilot plant or my convention reactor? So then, for instance, we use the singular kinetic paths. And what we see is that if you put the right constants into these two equations to get, sorry, there's a voice in the way. Sorry, if you use the right constant that you adjust them to use experimental data for both equations, then actually you can see that both equations, the Anderson-Dry and the Satterfield equation, follow the same singular kinetic path. So it's no wonder that they can predict equally well the data. Sometimes people say, no, look, this equation gives me a 0.996 R squared, and this one gives me a 0.992. So this one is the true mechanism, and this is the real kinetic equation. I think that's not true. That's a bit of rubbish. But what we consider for engineering purposes, you can use both equations with equal confidence. So this is one of the applications of the singular kinetic path. So, what about some other reactions then? There are some other cases in which there is thermodynamic equilibrium. One of the limitations of the singular kinetic path theory, and I think I neglected to tell you before, but two fixed points is the 0, point, because if after 3 meters of reaction the conversion is 0, it's sure going to be 0 after another 9 meters. It's there, the catalyst is there, whatever. And if your reaction is already 100% after 3 meters, you don't have 101% conversion. So these 2 points, 0, and 100, are fixed in the plot. But what if you have a system with thermodynamic limitation? I mean, your maximum conversion is 70% at these conditions. And you already have 50% after 1 second. After 4 seconds, you're not going to exceed your thermodynamic limitation. At most, we are going to approach it very closely. So then, that is one of the cases in which this technique will fail. What we did is that we used some data published in the literature by Froment. He published data on the conversion of, this was the dehydrogenation of ethanol. And he plotted conversion versus phase velocities, a whole family. So what we have to do is we have to transform this data into different temperatures and different phase velocities. So what we did is that we plotted his equations, the equation that he used to model this data into that simple model, and we validated that the model was working by predicting. The red points are the ones that we predicted using the simplified model, because in some cases we have to exceed this experimental range. So with this plot, we were happy that the model could predict from experimental data, and then we proceeded to construct a singular kinetic path plot of this data. And what we obtained, indeed, is that at a certain point, it begins to deviate. And obviously, if here, for instance, I don't know what is this, if at 250 degrees, the equilibrium is 40%, then you see that it's an extra gravity put on top of the gravity that you already have. That is like cheating. It's like saying that okay, is the case that the gravity increases as the pen is going up. It's not a constant gravity now. As it's going up, it's finding some kind of a new effect, which is the approach to equilibrium that is adding gravity on top of gravity, so the system doesn't work. So as you can see, it works. I calculated more or less. It is very close to your singular kinetic path line, up to conversion of about 80% are close to approach to equilibrium. After an 80% approach to equilibrium, it begins to deviate from the singular kinetic path. So, to solve this, what we say is, okay, instead of plotting the absolute conversion, what will happen if, in the example, the first example that I show you with H1 and H2, what will happen if I plot the percentage of the maximum conversion? In other words, if the maximum conversion is 60%, this 30% will be a 50% approach to equilibrium. So the 30 will become a 50. Do you understand? So if the equilibrium conversion is 80%, and I want to plot 20 and 40, 20 out of 8 is 25%, so I plot 25%, and the 40 out of 8 is 50%. So instead of plotting 20 and 40, I will plot 25 and 50. The percentage of the maximum approach, the percentage of the maximum conversion. And if we do that, then all the different cases, now they fall into the same line again. So then this technique, the singular kinetic path, can also be used when you have thermodynamic constraints. As a matter of fact, in the previous line, these deviations could be thermodynamic constraints, or you can be approaching a system, you can be approaching the regime in which mass transfer is becoming more and more dominant. So if you plot a quick, a few points on the singular kinetic path, and then one of the points get out of the line, then you can say, why is this happening? Okay, it's not thermodynamic equilibrium. Hey, maybe I'm into some kind of a mass transfer problem. Or if they fall on the other side of the line, hey, why is the conversion higher here now than the one predicted? What's going on? Maybe you have some hotspots inside of the atom. So the nice thing is that I think I like this better to see why the points don't fall into the line. It gives me more information as to why the points fall into the line. In any case, it does work with the dehydrogenation of ethanol to acetaldehyde. Now, what happens if you have a feed with different feed composition of different kind of reactants? I mean, the worst possible case could be the catalytic cracking of a gas oil. And then you have your paraffin, olefin, naphthenes, even some aromatics in some case. The paraffin will have a different cracking rate than the naphthenes or the olefins, than the isomers. The cracking rate is also a function of the carbon number. So it's a big mix there. So Nace published, I think it was in 1971, he published the conversion of 4 different gas oils. I mean, catalytic cracking of 4 different gas oils. The composition of these gas oils was different. What I liked was the fact that he published data different retention times. So, and I find a 4:1 ratio, so I plotted it and see what happened. In this case, you do not have thermodynamic constraints, obviously. So you just plot that straight the conversion. And what was very surprising is that the 4 different gas oils do follow the singular kinetic path, and that's in spite that the reactivity of each one was different. It's a bit difficult to explain, especially at the refinery people, because they say, how come it's impossible? But I think maybe you're comparing here, it's a relative comparison. I mean, high versus high, and low versus low, and medium versus medium. It's like you're using a ratio, you're not using the absolute numbers. Because when you do T1 versus T2, it's a ratio. So 200 over 100 gives you a ratio of 2, which is the same as 2 divided by 1 also gives you a ratio of 2. So it's a relative comparison, and perhaps that is why it does work in this extreme case. Now, there are some cases in which it doesn't work, or I think it doesn't work. The previous example that I showed was the dehydrogenation of ethanol. And Froment modeled his reaction using a Lamier-Hischenburg kind of equation. And there were three constants, and then in the same paper he also gave the relation between the constants and the temperature, which I used in the model. And we got a straight line. But this was the simple equation, the Fischer-Tropsch one, the iron one. If you do change the constant A, some people say, for instance, that the constant is, it is indeed a function of the temperature. We did find that for iron, it's not really. If it is a function of the temperature, it's a very weak function. But let's suppose that if it were a function of temperature, let's say that yes, it is a function of temperature. Then, as we change this constant here, the water, which is a product from the Fischer-Tropsch reaction, at the same time has a negative effect on the kinetic. So it is again like changing the gravity as you go along. And we see that by changing the constant A, we do have different paths. This is the worst case when it's zero. Now, fair enough, then what we can say is that for different feed composition, the singular kinetic path may not work for Lamier-Hischenburg kind of equations. That's the bad news. The good news is that because it doesn't work, or in this specific case, it was very useful. Because then when we have this figure, we said, hey, but look at this kinetic path. It's very similar to cobalt. Yeah, it's very similar to cobalt. That is very strange. And this one here is very similar to the kinetic path of Ledakowicz, when he tested an iron catalyst that has such a high water gas shift activity that water was not in the products. All the water was converted to CO2 and hydrogen. So you see, that sounds really strange. Then what makes it tick? Then we start plotting, comparing the singular kinetic paths of cobalt and iron. Then there was this cobalt manganese catalyst that, unlike other cobalt catalysts, did have water gas shift activity. And then we found that that cobalt manganese did follow the singular kinetic path of iron catalyst with water gas shift. So, but this kind of quick analysis, by looking at the shift in the singular kinetic path, we came to the conclusions. Actually, we were able to propose a unified approach to the Fischer-Tropsch kinetics, developing an equation that works with iron, with cobalt, with ruthenium, with all the metals. And it can explain also why there is some controversies in the literature. I mean, I cannot believe that that Satterfield and Buchur and Decker, that this kind of people will make mistakes when they do their kinetic equations, when they develop their kinetic equations. If Anderson just put the partial pressure of hydrogen, and Satterfield says, no, you must square it, I don't think that one of these two will be wrong. These are good people. To develop a kinetic equation is relatively easy. You just do your experimental design, you are sure that your GC is working properly and your computer is doing the right statistical regression, and there you have it. So why will there be such a big difference? The reason can be explained in terms that their catalyst is different. They have different catalysts, different promoters. Maybe they have the same catalyst but prepared in a different manner. Maybe they even prepare it in the same manner, but then they activated it in a different way. Maybe the linear velocity that they used for hydrogen during reduction was different. There was more oxidation, reduction, oxidation, and sintering in the surface. All this. The surface is the one that gives you the rate equation, the kinetic equation. You have a different surface, you have a different kinetic equation. So one can explain that the surfaces were different. That's why they came to the different kinetic expressions. Doesn't mean that one of them is wrong. The only thing that they're doing wrong is when they say kinetic expression for iron or kinetic expression for cobalt. They should say kinetic expression for my catalyst. Failure. If you want to use this, use it at your own risk. But in any case, coming back to the presentation, by looking at the singular kinetic path shape, you can see whether the catalyst is the same or not, whether it's a different catalyst. Or if you record some of your data points and you now are coming out, then you have problems in the surface of your catalyst, and you stop using that catalyst for kinetic studies or for kinetic selectivities unless you introduce a deactivation kind of parameter. So it's bad news on the one hand and good news on the other. And here, I'm just getting close to the end now. A few more minutes. We have a very simple reaction now. Now we're making the case general. I mean, I showed specific examples based on experimental data published in the literature. Now we're using this simple model also to generate new plots. This is A plus 2D goes to C plus D, and the rate is proportional to the concentration of the reactants, A times B. Now I'm using different ratios in the field of A and B. When that happens, I mean, the previous example of Fischer-Tropsch probably works so well because everybody is using a ratio of 2 to 1, or very close to 2 to 1. But if you have a ratio 0.3 or 3, that's a big deviation. Then you start getting away from the singular kinetic path again. So the way to come back is to do the same kind of approach that we did with the thermodynamic approach to thermodynamic equilibrium, and that is again plotting the conversion as the percentage of the maximum conversion, and then again you get to straight line, or not straight line, sorry, all the points follow into the same curve. For other kind of rates, same reaction, but the rate now is C8 times the square of P partial pressure of A times square of partial pressure of B. And also different ratios. You can see that again it deviates from the unique function, and again it goes back into the same function if you do indeed plot it as percentage of the maximum conversion at T1 and percentage of the maximum conversion at T2. So it does seems to be a kind of a general approach. So this takes care of the presentation, except that I'm going to give some, first I'm going to give some advantages and then some warnings. The advantages of this approach is that if you want to verify a kinetic behavior, the number of experiments that you have to do are far less, than following the traditional kinetic verification approach. It is a very fast analysis and gives you an insight into the catalyst reaction system, because when you do, traditionally, when you do kinetics or you try to test an equation, you plot it, you make a parity plot, predicted versus experimental, or predicted versus whatever was predicted by other equation. And you cannot really visualize what the difference is. But if you use a singular kinetic path, actually you can see this thing moving this way or that way. And actually you can see whether you're getting closer or further away. And then you can also, it gives you some insight into the catalyst and reactor system, because as the examples that I explained to you, you can see whether you have some kind of maybe mass transfer or thermodynamic equilibrium. You will know beforehand when you have mass transfer, when you have hot spots, whether your catalyst deactivate the surface. I mean, you want to do Fischer-Tropsch and you want to increase the partial pressure of water to 6 bars just to be sure that you have that term fully quantified for, but then you are oxidizing your surface. And it did happen many times, not to us, but it did. But it does happen. But this is just an example that I can think of. There may be other examples in which if you change you go to extreme condition just to prove your kinetics, you are altering the surface of the catalyst. It can give an insight into that. it allows you to identify the most appropriate kinetic equation in the literature for in-house catalysts. In other words, this is again that example. You prepare your catalyst in a different way, your kinetics is not the same, but then, luckily enough, it follows a different path, so you're not wrong, you're also right. It's applicable to fixed and slurry bed reactors for preliminary, you can use it for preliminary scaling up, but we did have quite a discussion of this theory with Professor Enrique Iglesias at Berkeley. He was very interested, and then he said he gave me last year in November, he went to South Africa, and he proved analytically that indeed there is a singular kinetic path for plug flow type of reactors. But he did prove that it wouldn't work for different feed compositions. So now he has to prove that when you standardize your data, it also works. He showed me, and that there is no mistakes there, he showed me that it would never work for the case of a CSTR reactor with different feed compositions. And I simulated that in the model, and indeed, you generate a family of curves. Same as in the case of Langmuir-Hishelwood kind of equations. So that is a limitation. Well, I think I'm jumping to the next. I'm jumping to the next transparency already. It does not work for CSTR reactors. Now, what surprises me a little bit is that the date of the dehydrogenation of ethanol is a Langmuir-Hishelwood kind of equation, and in some points in the first transparency that I put on the Fisher drops, two of the people that I quoted are CSTR reactors. So it seems that under certain conditions it also works for CSTR, but I didn't figure out yet under which conditions. And I haven't done much work on the SKP on CSTR reactors. So at this point in time, what I think I'm safe saying is that it shouldn't be applied to CSTR reactors. So I think that's. Thank you very much. I think that takes care of the presentation. Thank you for your attention and your please.
Any questions?
I'm a mechanical engineer and no chemist, but I have some questions. First, I like the analogy to the particle mechanics, that part. Now, would you expect to extend these kinetics to all kinds of? You said there are some limitations, and what's the reason for this limitation?
The limitation is in the CSTR reactors. The reason is that on the CSTR reactor, you have a unique relationship between the feed, the conversion level, and the partial pressure of the reactants. The partial pressure of the reactants do not change, like in a plug flow reactor, with the conversion level. It's a perfectly mixed reactor. So, for instance, the exit composition is the same as the reaction composition, and the reaction composition, you have your inlet feed composition, which you do not use for the kinetic analysis, but that inlet becomes immediately your reactant's composition, and that will depend on the conversion degree. So it's like a step function.
Okay, what if I close the inlet and outlet, make it a kind of a batch type of reactor?
Oh yes,
And that
a
will work.
batch will work. Yes.
So, if I understand you right,
time, yes.
this reaction function should work for all kinds of reactions.
Yes, it should work for all kind of reactions. As a matter of fact, I still have to get to the acknowledgements. I'd like to acknowledge. I'm grateful to Professor Iglesias for acting like a devil advocate, but in the process he proved that it works for some cases. And also Wim Mandersloot, former director of the CSIR, for interesting discussions about how to solve the approach to thermodynamic equilibrium. And you remind me of him because Wim was working on what? On sedimentation. Sedimentation. And then he said that in sedimentation there was a technique, not like this one, but in that technique you actually use the percentage of a maximum instead of the absolute numbers. And then he said that he could find an analogy between sedimentation and this singular kinetic path. And then is how we come to the conclusion. But yes, if there is analogies with other disciplines, yes, I think that safely I can say that one can indeed use it in all. Unless there are maybe some. One of the questions that they asked me is what will happen in an autocatalytic reaction where the products increase your rate of reaction. The product also helps the reactants to convert. And it also works because that is not that they will start doing so only after you have reached 50% conversion. After you have your first molecule of product, that first molecule will already help the other molecules to react, the other 99.999% of the molecule to react. So after at T1, you already have some of this autocatalytic effect, and it will be there at T2, and that follows its own singular path. So it also works for autocatalytic.
Okay, my second question would be, how do you use it? Let's say if I give you a plot, okay, I tell you this is the reaction path, and I give you a percentage plot. This is the universal percentage plot of a reaction. How do you use it? Can you extract all the information, the kinetic information you need from the plot?
Okay, there are different ways of using it. One of the ways is that you can do kinetic studies. If you need to know what is the kinetic of your system, you use this SKP to make sure that you have the right kinetics. Practical applications I can think of is an example that happened some years ago. And we were going to build a new pilot plant, slurry-based reactor. And then I cannot remember whether it was money or the height of the roof, but somebody told me, look, the height will have to be 3 meters shorter than what we thought. Tell me, can you still get relevant data? That person was really not into modeling, but it was a fair enough question. So I said, if the bed is 3 meters shorter, instead of the right, then this was to say, but wait, there is only one way in which the rate is going to decrease. So if I know the rate there, I can predict exactly 3 meters higher. But then the advantage is that even if I do not know my solubilities, my mass transfer limitation, problems with the temperature profiles, as long as they go in the same direction, all of this is taken care of by the relative nature of this comparison.
But can you go the other way around? If I just give you the plot, do you know the reaction?
The kinetics.
Yes. So let's say reaction order or whatever.
I think it is a bit dangerous to use it the other way around. What you can do the other way around is to say, this is the SKP plot, and this reaction and this rate expression also follow. I can use the rate expression with confidence for design purposes, but it doesn't mean that it reflects the real mechanism of your reaction.
This the rate or reaction rate may not be just this one. There may be other reaction.
One thing is that I don't think that this technique should be used for mechanistic studies. I don't think so.
Okay, but my last question would be, why do you choose the word singular?
Because there is only one path, one way for the reactants to deplete. And why did I use the name singular is because there is another concept that I haven't shown here. And actually it is that, let's say, I'm sorry, I'm going to use a funny transparency. This is the 0 point, and this is the conversion. Now here you have conversion versus residence time. Just conversion versus residence time. And let's say your final conversion is 80%. There is a transparency that is very similar to what I want to show you. it's better to use one of those. Otherwise, our imagination can
There's also a
carry out.
blackboard back there. There's a blackboard.
Oh, okay, thanks. Yeah, sorry. Okay, this conversion here, after 1.5, you reach a conversion of 27%. Yes? And this is the part. Huh? If I reach that 27% in a different, at this by changing my feed composition or my temperature, if I standardize this, I will always follow the same path. I will not go this way or I will not go this way. It's a singular path, only one way.
The reason I ask this is that when you use the word singular, whenever you just say a singular function or something,
Yes.
mathematically it has a
Yeah.
special meaning to that.
Yes,
So
I should
that's
have
why.
said unique
Yeah, unique maybe
Yes.
is a better. I mean,
instead of singular.
when
but
you say
I-
singular, I mean to a mechanical engineer, okay, the function has some points,
Yes.
has a special property
Yeah,
to it
yeah.
or something.
The singularity.
Depends.
I realized that. But that's yes, I didn't realize that at the point in time. I said there is only one way, and I also admit my English is not precisely 100%. So I said, oh, singular. I should have said unique. You're right.
For Langley-Hinshelwood kinetics, you showed that the curves deviate from
Yes.
singular. What if you plot the percentage of maximum conversion? Do they come together?
Yeah,
or
no.
They do come together.
They don't. I tried just last week, but now I'm sure there is some kind of thing that one can do, but I haven't really got to do it.
The reason you gave for the CSTR not working, is it that and not the residence time spread that you get? Does the residence time distribution make any difference? The next question, if it only works for plug flow, what happens if we got two CSTRs? With a
Well,
different
actually,
distribution?
I like that explanation because it could be. It could very well be. Some other CSTR data where I used just the residence time, it does sort of.
Do you not have a unique
Yeah.
time for each bit? And
Yes.
If it doesn't work for CSTR, then it can't work for something that's slightly away from a plug flow.
Yeah. As I said, that limitation is just for the present. I think I'm going to play around with the CSTRs a little bit more. I didn't pay much attention to them until Iglesia said no, it would never work here.
And that was enough challenge.
Such an approach should work for equally well for, let's say, heat transfer or mass transfer. I mean, aside from kinetics, because the way the equations are set up is quite similar.
Yeah,
So,
yeah, probably it will work here. Probably. I really haven't. Yes.
So this kind of kinetics basically for the design purpose or also for the control purpose. Can you use this for the control purpose?
Control. I mean, sorry, but what do you want to control now?
No, I just because I did something very similar for that's for wood chip, the pulp and paper, and I use those kind of kinetics and because I want to control my product, the final product,
Yes.
and I have a lot of parameters.
Oh, yes.
Okay, so I change the parameter every time because I take a sample, I got some, then I change the parameter. Then this kinetic will fit the specific condition now. So I'm thinking in the reactor, this kind of equation will change with time when the reaction keep going, or they are a constant, all the parameters are.
It changes if the catalyst deactivates.
Yeah.
If there is a change in the catalyst in the surface,
Mhm.
then your ratio will be different.
Yeah.
I mean, look, you can have your conversion in a reactor.
The switch over there. the other one's the light training. The light.
Okay, let's say you have here your conversion 1 and your conversion 2. Yeah? Now you have your singular kinetic part. And then you say, fine, I have here in this point 10% and here 40%. Is it good? Yeah, everything is still all right. But I have 40 and 90. Is it all right? You may have increased the temperature. Yeah? 40 and 90, yeah, well, 69, yeah, still all right, no problem. Now you change your temperature, or you change any other parameter that will change, make the conversion change. Then you say, okay, now I have a 30 and 70. Is it all right? Oops, something has happened. Something has happened. I mean, that's, if you say control purposes, yeah. So if you have a lot of variables, a lot of variables, and when you change all these variables, it will give you different results. And how do you know whether these results are good? Some change didn't happen to your system. If you use some kind of, if you know that there is some equation that defines the ratio of your result under different conditions, then you can see whether you are out of the so-called normal behavior. That's like
But when you shift down, did you try to find another curve to fit it?
as long as that change is always there, it will always be there.
Yes.
Yeah, then you find
Did you
out.
try to do that? That's why it's a control purpose. Maybe, okay, once they shift, then you have a new curve to fit it in this moment.
Yeah, look.
Then you can, maybe can help you, or we shall increase temperature now, or
Yeah.
we shall increase the, decrease the flow rate. And,
Yeah, you can change the curves. I mean, in our case, we can change the catalyst, or our catalyst may deactivate.
we are that very difficult, very easy. Can you do that on time in situ?
Pardon?
Can you do that in situ? Just they have one curve initial. Okay, for certain times the catalyst may be deactive. So the really the curve won't explain what happened now. The curve must shift down because the parameter change. Is that easy to do? You just have some data from the reactor, then I put in the computer, then the new curve will come out.
Yeah.
Is that possible? Very correct.
You keep measuring the two conversions at two different points.
Yeah,